computer the right way. I'll tell you a story here. When I was putting through the slide, my 6-year-old came by and he had a very hard problem kind of relating to why 2 plus 2 is 5. And he continuously asked me, 2 plus 2 is not 5, 2 plus 2 is not 5. But he has a point, right? And that my 6-year-old is not very dissimilar to all the software engineers. We have a building of trust. We have built that notion that hardware is trust, like computation is trustworthy among a lot of like community, right? And my 6-year-old is right, the software engineers are right. Finding out reliability problems and designing for them needs to kind of happen at different levels of the stack, and we need to hold accuracy important in computation. So the Zoom thing. By now we should be getting used to it. So what are silent data corruptions? They are defects in silicon. They happen at the hardware level. Hardware thinks it's doing the right thing. It's extremely hard to detect. So a lot of people in like places like Meta, Google, spend their time trying to like figure out what the heck went wrong with this hardware, right? It can go undetected for months or years because we don't have a trace of them in our fleet. And then when we find it, we need to trace them back. And it has a significant impact on services. Remember that our end customers, all of us using our services, need to have trustworthy computing come to them, right? So that has a significant impact on services. But you're going to say, I think a lot of us know in the audience and everywhere, say, but wait, cosmic rays, right? We had a lot of work on software. We did a lot of research and really good follow-up work on them. But there is an important distinction. The cosmic ray-induced falls were very, very rare, right? They do happen, but they were very, very rare, and it's 1 in a million. So when I click the next thing, you're going to see silent data corruption. These are 1 in 1,000. They are multiple orders of magnitude different, and they are not your 1 in a million error that we can like ignore anymore. So why didn't we find it? We're going to talk about in this panel. But also remember that at scale, when we have millions and millions of CPUs, you can test for these kind of things and actually prove what numbers you are actually seeing. And our story, our story started like that, right? So when we encountered one of them, we had the same approach. We said, hey, look, this is very rare. This is going to be like, cosmic rays. It's not going to be, really prevalent in a fleet. And our vendors said that. 2 of them are here in the panel with me, and I can talk about this now because they have worked along with us. But in the beginning, nobody's going to say, hey, yeah, you're getting all these errors. What do you do about it? So this is a needle in a haystack situation because these are silent. Remember that we don't have any trace. We're not able to track them. It's happening in compute elements, silicon. We don't have any record of them. And we are trying to find them at different data paths, different operating conditions. And the needle in this analogy keeps on moving between different places across the fleet. So it's extremely hard to find another silent error, silent data corruption very reliably in a large fleet. So what did we do? We ended up building directed tests. This is in our paper, so I'm not going to go over that. But this shows an example of how we took from the application level down to an assembly level reproducer. And we didn't stop with that. We ran the reproducer across our entire fleet, right? And then we were able to find that it's not 1 in a million. It's not, a rare occurrence. We are finding hundreds of them, right? So that's significant. When you're finding a lot of data corruptions with no checks in the fleet, that is a significant problem for hyperscalers or like end customers. So we have 2 different ways we ran it, right? Because when we started finding it, the running in the fleet is also a research problem, right? How are you able to find the time to run these reproducers in the fleet? These are not, your workloads. They are not services. We need to run them in the fleet, and we had 2 ways of doing it. One, we ran, something called fleet scanner. This is similar to taking pit stops when you're running like F1 or like any car race. When the mission is not in production stage, you run tests at them. And we were able to run a lot of them. We found hundreds of missions, right? So that's the first clue for us that this is not a rare occurrence anymore. This is similar to any of the errors that you will get in your fleet, right? But then this was, the Zoom thing keeps changing. But this is too slow across a live fleet because we don't want our fleet to be in non-production states a lot of times, and it's hard to converge across a large fleet. So we did the next best thing. We co-located running directed intrusive tests along with our workloads. This is a challenging thing to do in our fleet. We need to know our fleet really well, coordinate and schedule these tests to run across an entire fleet. But what it does for us is really get a lot of coverage, because now you're running really, really small, really directed tests, but you're running it live without waiting for missions to go to a non-production state. Again, this is also a paper that is out there that you can read, so I'm not going to go deep. But with all these things, we are able to find that issues happen 1 in 1,000, right? It's 1,000 DPPM is defects per million. And we are able to find it's 1,000. It's not like 1, it's not 2, it's not something that you can ignore. It's not something you can just chalk up to cosmic rays. There's a lot of things that have changed in how silicon is produced, manufactured, or built. And the rest of the panelists will talk more about that. But what really scares me for this problem is we don't know what this could be. We don't know how much silent errors are there in the field. We need different ways to tackle them, software application strategies. We need production fleet methodologies, scheduling, coordination, orchestration. We need hardware design, and we need a lot more research and collaboration. I want to leave you with just this. Silent errors that we are finding in our fleet are not, like 1 in a million, not very rare anymore. They are significant time spent by hyperscalers, and it's a foundational computing problem because we need trust. And this occurring at this magnitude is very hard to trust for our application developers. So we also did something recently. We did an RFP to promote a lot more academic collaborations. We announced the awardees. One of them is in the stage with me, Carolyn, and many more in the audience. So thank you again. And I'm going to pass on next to Ronak from Intel. So.
Thank you. So I'm going to talk a little bit about is from the silicon vendor perspective, what we've experienced working with our customers and improving and recognizing issues that we've had today. You'll see my counterpart from Angie will tell a very similar story as we go through this. I think the first question you get asked is, why is this happening now? What is new that's causing this? And part of it is to recognize that it's not new. This phenomenon has been there forever. And we have people in other industries who have recognized this. You have the automotive side, the aeronautics side, the financial side, that does things like redundancy, and they've done it for decades because they recognize in order to guarantee correctness, it sometimes takes that level of redundancy. I think the thing that has changed now is the scale at which we're doing the computing. You want to move to the it's the scale that we are doing the computing on, especially at the hyperscale, where we have millions, if not more, machines running together now. And you have the ability to separate the noise on if something happening and actually find a sticky. Find that case where it may have looked like it could have been a software event, it could have been some sort of random occurrence. Instead, now you're seeing something that you're able to actually detect. And when you run that scan, you can see this happening on more than a single machine. And I think that's been the key learning, especially as the hyperscalers start to run services where they actually are now counting on that mission critical piece. If you go back 10, 15 years, into the early days of, say, Facebook and Google, when we would talk to them as our customer, and we would talk to them about reliability features, I think back then their view was, these are features that high-end computing needs. They're not features that we need. Why do we need some of this, I'll call fancy stuff that you have? Whereas if you come to today, I would say that the mission critical, what we used to call mission critical features, are now essentially the baseline for many of our cloud customers. And so internalizing that that's now the requirement across data center computing is very, very important for us to recognize. So when we look at the problem happens at all different levels of the system. It's the CPU itself, it's memory, and we're not going to talk probably too much about memory today, but memory is a whole class of its own, and it's the rest of the system as well. And it's about detection, it's about what to do once you detect something, and it's also about updating your system. In some of these cases, we've also found ways to work around issues. But working around them typically requires things like a firmware update. How can you provide those updates without interrupting the ability for a customer to provide a service? And so these are all the different levels that we think about as we go through this process. So if you look at what are we doing proactively, obviously we've always had things like protection within the processor itself. These could be things like pairing, they could be things like ECC, it could be redundancy within functional units, redundancy between ports. You know, if you think about redundancy, people have done redundancy at system level for a long time. As we increase the number of cores in the system, you're going to see people, I think, do more and more redundancy between cores. Things like lockstep between cores becomes much more powerful when you're stealing, say, 1 core out of 100. It's 1% of your compute power versus when it was 1 core out of 2 or 4. We're also going to start offering the ability for people to run our internal tests at a customer. This is what we're calling in-field scan. Take our scan content that we run at time of manufacturing and have the ability for a customer to run that same scan content in production in their data set, either as they're moving processors into production or while they're in production. Think about the fleet scanner that Meta talked about. And so over time, you can continue to check your processor and do it in a way based on the test that the manufacturer has provided. And then we can augment that with additional tests, just like the ones that are being used today. And so it gives us a more robust way to actually identify where you have parts that may be susceptible to some of these issues. Obviously, when we're doing our testing manufacturing, like I said, it's about all the different pieces of silicon. It's not just the CPU. The CPU has obviously been a big area of focus, but it can be about any accelerator, it can be about your NIC, about your smart NIC, or any of these things. So any of the concepts we're talking about today apply in general to silicon, not just about the CPU. Like I said, we'll have things that we'll do on our manufacturing side that we do at the time of when we do our traditional burn-in, when we do our traditional testing. And then we work with our partners, whether it's somebody who is putting together the systems for our customers, or the customers themselves, they do their own. They may be doing extended burn-in or expanded testing that better mimics their use conditions. And then we are advocating to our customers to be able to do this continuous scanning, just like you heard that Meta is doing. So that even if a part looks good on one day, if something happens over time, and we tend to see this, it's not about wearing necessarily, it's where you may have circuits, for instance, that were weak. And if by running those different use cases, they end up failing. You want to be continuously testing if you have systems in this space. So how do we provide tests to make it, one, that they can capture them, and two, they can be run in a non-invasive manner. And then finally, the last part I'm going to talk about is how do we allow this to become something that others can contribute to? And this gets to what we're calling our open data center diagnostic project. Move to the last page. So one of the things that we have now started is if you go to GitHub, you'll see that we have this open data center diagnostics. And this essentially is the ability for everybody to contribute tests to the mechanisms that we use for looking at our CPUs and understanding where we may have the ability to build a more robust suite for what we're doing. And so we've started to partner with some of our friends, both on the industry side as well as on the academic side, to build out this infrastructure and use this as a way to essentially crowdsource improvements in the way that we're doing our testing. So as you're looking at different research projects, for instance, I encourage people to go take a look at what we already have there and use that as a starting point to understand both what have we already found as areas to focus on, and then where are the opportunities to improve on what we're doing. Because I think one of the things you'll hear from all of us is we would like to see more investment from the research side into these problems, because these are real problems impacting computing today at an industrial level. And so there's a great opportunity here for us to improve the way that we're working together. So with that, I can hand it on to my colleague.
So, hi folks, my name is Subhankar Murthy. I'm an architect and PhD. So I'm just on behalf of our law team. So So high level positions we computing SPCs are model. But SPCs are simple and underlying problems. So in order to first we need to understand the two process, right? And I know I'm not done with the position statement is going to be also what can we do to design the walls. And I agree with what Ron said. Last slide, addressing this is really across the stack, right? Across all aspects of design, as well as testing. It's required to actually address the SPC problem. And I'll talk a little bit about some opportunities on how the computer community can help with this as we move forward. So one thing I want to talk about is we can actually I want to give a little bit of a perspective here on this topic because there's a similarity to what we are facing now to something which happened around the time that I got interested in working class right? So let's talk about software as Sriram said, we are not talking about software, there's a problem. If you look at the problem, like softwares are well known, like we reported incidents of the published incidents of software. But really, when this became a burning issue for like across the technical community, was around 2 decades ago when systems, user services at scale, what scale looked like back then, were getting impacted. And there was discussion to what is happening, why are we getting what do we understand? This really galvanized the community together and the architecture community as well as other technical communities to understand the root cause of this problem and drive a lot of research in fault modeling, as well as taking well-known fault tolerance techniques by blocks and figuring out how do you make them efficient and applicable to a broader set of servers as they were used, right? And just talking about sampling of paper, this is already got the papers, and around 2005, the technical communities interested in this problem came together with the Chelsea workshop to actually work together, work deeply together, industry and academia to try towards it. And now what the result is a set of industry best practices to deal with the soft error problem, and it was immensely valuable to come together. Right? And this is like I think there's just a template that we can work off on. So next one. So why are we talking about SPCs now? Right? So one of the things we see is that as we are moving towards this model, like what the previous speaker said, we see defense, and especially we have seen marginally, so these are defenses who activate all under a variety of very specific operating conditions like voltage and workloads and things like that. So really what we're talking about now, software is used to run transit. Now we're talking about it. So it's a different form. So testing is extremely important. Like we follow all the best practices as well. All the way testing from maybe manufacturing testing to supporting our customers with in-field testing. We have diagnostic we have already talked about it. But exhaustive testing of market testing alone is going to be very challenging because we're taking the process designs and trying to find marginalities in designated qualities is very challenging too. So you need to also think about what can we do level of design, what can we do to architect towards things which can cope with this issue. And so marginalities is one thing, but we also have this ability and degradation. In fact, there was a whole a lot of reliability research along with software research going on as well. And one of the ways this is well known is by archiving an approach, always a performance. So we have to get the balance. So what do we do about architecture for resiliency? So really the thing is we like to architect resiliency with minimum performance and energy overhead. What does minimum mean? So how do we architect towards this goal? So there is the prior body of research that we did wrote the word actual solution of self gives us some ideas of things that we can do. So one is to develop architectural level fault models for SPC positive faults. So you can think of it like things like vulnerable impact, like AVM modeling is tremendously useful for industry to write over how do you architect for software force and some early stage design and I think there's a need for things like that. Right? There's also a development of low-cost resilience techniques. So again, I think there is quite a body of work as well as demonstrated proofs of concept from various silicon companies on top of computing, and really customers how do you adapt them, make them practical to address these emerging defects, these models as well as techniques that actually pinpoint where these are happening and be able to isolate, right, so that we can actually design silicon clusters. So how can we work together? So I mean, this panel is great in some prior panels and some of the again, if you go back to how the community work together, I think having more deeper, longer, more sustained efforts to try to let's work towards that. And one other thing is, again, the new problems that just pop up from it's really hard for industry to provide all the data regarding all of them out into the public world effectively. So again, one of the things, it's audience is I'm spending some time try to understand what we do. And then let's figure out, like, let's talk about things we can do now to enable about also, try to figure out what we can do to actually find ways to do it and how to bring it out into the outside so that we can engage the outside community in general. Look forward to ideas, here in the panel and general, and how to deal.
Thank you.
And my name is Sean Blanton. I am a chief professor at ISCA at Carnegie Mellon University, and I'm very happy to be here with what some call silent data corruptions, others silent data errors. Here I'm showing you a simple timeline divided by t less than 0, t greater than 0. And at the bottom of this timeline, I'm showing you that, or the top of this timeline, I'm showing the different categories of failure sources for silicon. Right? We can think design bugs, application defects, right? And the categories of techniques for finding solutions to these issues, also the validation and manufacturing tests. Now, if you don't get all the defects, t less than 0, they're going to escape. That's a bad thing. These customers will have to do with that. And the techniques that are usually put in place fall into 4 different categories. We got acceptance testing, offline testing, online testing, and worse is to use application finding the defects or other errors that are creeping up from, say, early life failures or failures. Now, given I'm a test guy, my background is test diagnosis, I want to focus a little bit on the defect escapes. And it's been reported from companies like Google, Meta, Intel, and so on that they have figured out a lot of reasons that's coming up in a lot of those data errors stem from defects that escaping. So I'm going to tell you a little bit about an experiment that we conducted a couple of months ago with data that we have from our commercial partners. It happens to be a 14-nanometer test chip. We actually have to design because it's a test chip, so there's no proprietary information to keep away. It's pretty large by academic standards at 84 billion cells. If you didn't know, test chips are actually designed to be very well tested. So the test set that they use for manufacturing tests achieve a very high fault coverage for a couple of metrics, silverware and stuff. And we have over 30,000 fail logs for the computer question. Where a fail log is basically the data that you collect from a chip that's actually failing to manufacture tests. Right, so we sampled about 10% of these fail logs randomly and basically conducted the experiment that's described by the histogram. So essentially what we've done is that, for example, stuck-in clocks, we false simulated stuck-in clocks to get a gas cell signature. All that simply means is that you insert the fault or inject the fault to design, we simulate that, and you can end up with the impact of the fault on the response created by the circuit. What we found is that 4% of stuck-in behavior is actually found in the real defects. So it means that if we're using stuck-in only, all the other defects are getting detected for 2%. right? They're not matching particular model. If you go to somewhere, which is very popular nowadays, the number jumps a little bit to 7%. You go to gate exhaustion, where every cell in the design is exhaustively tested, it jumps up to 84%. But we're using a different metric that I'll show you in a minute. It allows us to jump up to 99%. And what this means is that as the number of intrusives, you have a model that more matches the behavior that you're observing on the test. So look what we're doing, we call pepper, single exhaustive test of physical regions. So we're actually dicing up the wafer into multi-layer regions and producing or inferring from those regions a circuit. And that circuit be, basically anything, not interconnected necessarily, and we exhaustively test those subcircuits. It's a very expensive process, but you see the change in the coverage of actual behaviors. So there's a lot that being gained by the test, but I am a believer that all the methods we're talking about are going to be needed to deal with software. So we get it here.
Thank you.
Hi everyone, so I'm Caroline Tribble. I'm at Stanford in the CS, the Department of an Assistant Professor, and I'm going to talk a little bit about system level testing for satellite data cards. So what's the state of the art in post-silicon manufacturing tests? One thing people will do, which Sean just talked about, is low-level scan chain testing. So we're going to modify ISC's flip-flops to enable them to accept external testing and ISC input. This is a nice technique because it's static. It's backed by automated test pattern generation, and as a result, it supports reasoning about coverage metrics quite scalable. On the other hand, another thing companies will do, hardware companies, is system-level functional testing. These are largely handcrafted, proprietary to the vendor tests. As a result, it's somewhat difficult to attain high coverage with in a scalable way. I'll speak about more maybe by that on the panel. But both of these have been shown to be useful and necessary for detecting faults post-silicon at manufacturing testing. So clearly we have issues because we have SDCs that are slipping through the cracks. So what can we do? One thing we can do is try to improve scan chain testing, and Sean talked a little bit about that. Another thing we can try and do is improve system-level functional tests, and that's what I'll focus on. So the benefits of this direction, first of all, are if you design really great system-level functional tests, it might be more convenient to schedule online in data center setting. On the one hand, if we can derive system-level functional tests from data center applications, the tests themselves can do useful work, making them less intrusive. And then on the other hand, if we can derive system-level tests from our scalable models or other hardware models, we can more scalably achieve high coverage. And as I mentioned, the Silly Fuzz paper from Google is a really nice example of this latter point. So basically, they use fuzzing coverage on a hardware emulator as a proxy for fuzzing coverage on the CPU. They obtain some really cool So I kind of just stepped through a couple of challenges to developing good, synthesizing good system-level tests and paint out the possible solutions. So one challenge to system-level testing is high error detection latencies. So error detection latency is the time elapsed between the occurrence of an error caused by a bug and its manifestation as system-level failure. One side effect of high error detection latency is error masking. So intuitively, in every cycle that goes by after bugs occurred and you don't detect or errors occurred, you don't detect that error, there's a non-zero probability that the error will get masked and won't detect it. Another challenge that results from higher detection latencies is that it's really difficult to localize the root cause bugs, especially when we have these bug traces that are on the order of billions of cycles. And some interesting work we can sort of look to from the post-silicon validation space to try and address part of this problem of higher detection latencies. It's called QED, so error detection. So basically, they look at trying to reduce error detection latencies by more frequently checking for the presence of errors during post-silicon validation testing. Another challenge is that it's not totally clear to what degree functional tests used by industry are representative of the at-scale workloads that are being run by hyperscale. And related to this point, ideally, you could draw a system-level test from some instruction or functional distribution that closely manages different data center system load, so you can focus our validation efforts on execution scenarios that hyperscale care about most. Related to this point, it would also be nice if we could adapt data center applications themselves to do self-testing so that we can overlap testing moving forward. And so this latter point brings up the question then of, we want to have applications themselves doing some testing, how can we schedulers to trade off the amount of system level testing we're performing based on the application resiliency requirements or QoS requirements. And then the third issue is actually something more like lack of scalable coverage metrics. So in particular, we ideally like to derive system level tests from RTL level fault models or other hardware models. And a lot of prior work has been put into this space, a lot of work by Jake Abraham in particular, to try and translate these hardware level faults into system level tests that can detect them. And this has been met with a lot of scalability challenges, and I'm going to talk about more on the panel. But I think that there's some renewed hope here, given some recent advances in formal verification of processor and accelerator designs, particularly some work that uses functional consistency checking, in combination with bounded model checking, find functional bugs. The reason why this is such a nice there's such a nice connection between these two, and why I think this opens up some new hope here, is that this functional consistency property is very nicely decomposable. So we don't have to analyze the whole circuit all at once monolithically, which tends to have a lot of scalability challenges. We can break up the design into a bunch of modules and analyze it individually. So ultimately, we need a layered approach. We need in-field scan team style testing. That's the CAS approach mentioned above here. We also need system level testing, but we can't keep on the same status quo. We need to look at things like QED derivatives of system level testing, revisit RTL driven functional test generation, look at how do we schedule these tests online in the data center throughout the lifetime of the hardware design. And then it's likely that these hardware designs are going to be so complex, we're not going to be able to catch everything with testing. And so then we need to rethink resilience and fault tolerance techniques and think about, do they change into setting? What can we repurpose that we've already designed and done?
Thank you.
So I don't have any slides present the perspective of the customers here. So we heard a lot of very interesting stuff from the vendors as to what they are doing, and also from Sean and Caroline as to what the research community is doing to improve testing. And the question that I sort of ask myself is what we have heard enough to solve this problem? Right? First, the problem is clearly very real, very, very big, and very difficult to solve. And the answers are not sure whether this will be enough to solve the problem. There's some real issues here. So I'll present to you some of the challenges that the customers and hyperscalers and what kind of challenges they are facing, and why this is too critical for the entire community to get knowledge. So first is, I think, the gap of what is needed and what exists in the state of the art is very real. Otherwise, we won't be having this kind of panel discussion. And the key picture I would sort of lean on is what Sriram showed the iceberg. Is what we see from the iceberg is 1 in 1,000, which is at the top. But what we don't know is how big is the gap that is under the ocean. So how big is really the iceberg? And what fraction of it are we able to see? So my conjecture is that what we're able to see is only a small part of the bigger problem. And hence, this is a really serious issue that we should sort of all get engaged and actively address. So, what is at stake really here is, I think, the trust of our users. Right? If I were to tell you that 1 in 1,000 planes is going to crash, none of us would get on the plane. Right? So, Ron mentioned that this is a well-known problem. It's not that this problem has not been known. But what has not been known is the magnitude of the problem. We were always told it's a 1 in a million thing. So I think that is different. And what the data shows is the problem is really far worse and requires sort of deep attention from all of us to engage to address this problem. So I also want to touch on what is the cost of some of these challenges that we are facing. Right? And the first cost is, of course, of software engineers spending time debugging problems. What they believe is their code, because it's harder bugs are supposed to be 1 million. And they spend months chasing what they think is a bug in their code, only to realize that it's a harder bug. Now, what happens is, if this happens often enough, engineers will stop debugging them harder to debug software problems, saying it must be the hard. Pretty soon, all the infrastructure will start to deteriorate. Very, very hard to recover from those habits. So this is the real challenge. Another challenge is, when you have corruption, there can be a serious consequence in terms of recovering lost data. So imagine your security key got corrupted, or your metadata in your file system got corrupted. Right? Those are very big issues because they amplify the damage that can be done to the rest of your infrastructure. And recovering from those is often very, very expensive. Right? So these are some of the things that we should sort of take into account, that this problem needs to be dealt at all levels. Right? So one of the things that, as an example, I'll tell you is there are many systems, there was logs, there was spanner database, and big table, all finding very rare bugs that seem to occur. Where they check some of their replicas were not matching. But one hint that finally came about after months of debugging was that the mismatch is always occurring on the same machine. So when workloads move, they saw this kind of happen, and then from the same machine, they isolated to the same code that is always causing corruption. So that gave a hint. Maybe the hardware is bad, and that's how sort of this whole area got sort of very deep in trouble. But it also gave hints as to how we can go about solving this. So if you can keep track of where they are seeing crashes, common crashes, and if they're concentrated on a code, that could be a hint that hey, this hardware is bad. So we need more methods beyond the ones that Sean is doing with the increased, pseudo exhaustive searches or system level tests that Caroline is talking about. We need a lot more creative techniques with which we can diagnose these kind of problems and sort of improve our technology from an end-to-end perspective. The other is the cost of actually the performance cost. We talked a little bit about in-situ testing of new tests that come about. These are very, very expensive to do because they affect production workloads, are often not very basic. So the key point I want to make is the problem is real, the gap is huge, and we need an end-to-end solution for this, which means we need the entire community to get it. Computer architects have to get better at more reliable architectures. The DSP engineers have to get better at providing better design for tests. We need better telemetry. We need better localization, which Caroline talked about. All of these methods, and then we also need the compiler and the software engineers to get better at writing code that is resilient against these failures. So we need everyone to get engaged and sort of figure out the most comprehensive way to address this more reliably. So the one thing that I think I would like to see as an outcome is for a common framework for infrastructure for all researchers, academicians, and the industry to be able to get access to some of these machines which are known bad parts. So we can convert these to high-value parts by making it available to the community and say, hey, go ahead and experiment tables, right? And we can release the logs of all the tests that were run to verify that these are bad machines. So some of these could be ones that have very large time to failure. And so the folks that work on figuring out how to write better tests can see how can we reduce the time to failure? How can we improve localization? Right? What are the methods can we bring to bear to solve this problem? And so think of it like the Netflix challenge that was there to build a recommendation system that improved the recommendations that were provided to users And because we are an open competition, and that competition helps spur a huge number of innovations and recommendation systems. So my hope is that enabling this infrastructure, open infrastructure, and for that, huge thanks to Rona for this open DC diagrams and making some of these machines available. We need to do a lot more of that. And if we can build a common infrastructure for an entire community and enable it to be sort of accessible to all, with all the shared research, so everyone can build on each other's work and verify and validate each other's approaches, I think we'll make substantial progress in this. That's my hope. Thank you.
Thank you, Rama. For the next stage, we'll move into kind of some of the questions between the panel, because I was listening to some of these perspectives, right? But I want to take the hard customer view and ask really, what did we miss? Why are we here? I mean, 1 in 1,000. Rama, you pointed out some of the costs. Like Ronak, you talked about some of the like investigations and tools that we have. We have a lot of things that we are doing, but we are still finding them. And we talk about the tip of the iceberg. Why did we end up here? And because Rama, you went last, I'll let you start. Did we miss something? I mean, I'll relate a personable thing, right? In the hyperscale kind of environment, when we have millions of them, it's probably easy to go turn around and like kind of, run these tests and tell what the number of issues we have are. But maybe we missed something. Maybe we didn't look at something that we should have looked at. So while we figure it out. Rama, why don't you go first? And then I'm going to ask Sean and Carolyn to come right after with the testing. Did we miss testing? Did we miss? What did we miss?
Oftentimes we have a data set, let's say, of a few thousand machines, and you find one bad one. You don't sort of think it's very significant. You just return it and get a replacement over that. When you have a hyperscale and you see a very large fraction of those issues showing up, you notice something statistically significant happening. And I think we started seeing this about 3+ years back, where we were able to debug some of the problems that we were seeing. We thought the software bugs. Eventually, we were able to get into a hardware bug and convince that there was a problem. Then we sort of tried to evaluate how bad the problem is. And every time we looked at it, we found the problem being worse than what we thought it was. Right? So I think we ended up here because we were never looking at it at the scale that it needed to be looked at for it to be statistically noticed as being a significant challenge.
Thanks, Shaman. I can add to that. Right? So when we noted the first paper, Google immediately followed up with that paper on Mercury or Course. That was a really good testament that this is a problem that we are both seeing in our fields, and so are other hyperscalers, right? So it's important to know. So what did we miss on testing? I think you presented 2 different testing approaches. Sean, you presented very big like system level testing. Carolyn, what did we miss? Sean, why don't you go first, and then Carolyn comes forward.
So, let me give you an analogy of how we test and chip to the back. Imagine going to your physician and you're feeling sick, and the physician runs the test and says, yes, you're sick. Why? What diagnosis or diagnostic or what happened? That's what happens in manufacturing tests. We don't go back and look at what happened. So when you don't do that, there can be times where something is happening in a different location, whether it's in the chip or in the wafer, that we're not actually detecting. So I think more knowledge about what's actually happening at the defect level will help this problem a great deal.
One thing I can add on is that to go back to this sort of RTL-driven functional test generation I mentioned. It's sort of why has it been so hard in the past, and then why do I think we can do it now? So there's been a lot of work that demonstrates that software level fall models are not very accurate representations of RTL level fall models or RTL faults. And so there's been a lot of work that tries to translate RTL level faults. Like I said, a lot of by Jacob Abraham in particular and collaborators that tries to translate these RTL level faults into functional tests that can detect them. And so people were doing this with simulation and relation-based approaches originally. Nice 2010, 2013 back paper that talks about this. There's also been approaches used methods to do it. So we use bounded model checking, backed by SMT solvers to translate these RTL fault models into system level tests. But the problem with all those techniques is they all face a lot of scalability challenges. There's been some recent work by Frank Barrett and Stretchy Teacher at Stanford, also Wolfgang Kuhn at Kaiserslautern started doing work in this area as well. We're using functional consistency checking in combination with bounded model checking in order to try and detect functional bugs in processors and accelerators. And a really nice thing I mentioned here before about this property is functional consistency property. While it is a very general property, so it's not necessarily going to catch every bug. So if you have the functional consistency, it's just the same instructions and same inputs, you're checking to see if your hardware will always produce the same output. So if your hardware always produces the same incorrect output, you would catch that certain bug. Functional consistency check, you can catch a lot of bugs this way though. And this functional consistency property is actually decomposable. You can analyze the arbitrary hardware module the same way that you can analyze those. And so because we can sort of do this much more scalable functional verification of processors, it seems like we might be able to use those techniques to translate these artificial models into better functional tests. We're able to create sort of artisanal techniques to do it.
Awesome. So, but I want to go back to silicon manufacturers also, right? Because this is not just scale. This is not just testing gaps. Rona Sudanva, what do you think? Silicon manufacturers, because I'm sure Google or Meta come to you and said, hey, this is not acceptable numbers, right? What do you do? Where are the misses from a silicon manufacturer standpoint?
Let me give a specific example. They have as features in them, and they were driven, the design has been driven by software as the thing that you need for technical. Now, when this started happening in the field, right, so you notice that certain parts are having these, we just call it functions or something else. First thing we've done is we did DFA. DFA is physical failure analysis of these parts, and one of the marginal defects that we see in the field are small delay defects, right? And small delay defects is something that the product was not designed on. Right? So that gives us information to go back and say, okay, let's go back to the loop. Let's try to close the loop. So this involves, for example, if you do something like ATPG, it's not just tech fault model, now it's a delay fault. Right? So you have to ask about transition delay faults, path delay faults, the cost of testing for small delay defects is quite large because now you need to look at the minimal snapshots, not the maximal snapshots. You have to look at all the log ones. And when we have a high performance store, we have a lot of rainflow paths which are happening personally. So there's a testing aspect there to be done. Now that we have also understanding of this, we have a tool called UV field health checks. It's very similar to the VC diet that Ron mentioned. It's a set of tests that we provide to our customers which are testing for it's basically looking for things like marginalities, and now that we have understanding, those are actually being adapted as well to accommodate this knowledge that we have, right? So it sort of ripples through from testing to now into design as well. It's like now we have a default mode. How do we design for that? Right? So the silicon design, the RAS design is also influenced by the knowledge.
Yeah, I want to go to that design piece, right? Because if you design a part that has this many DPPM in the fleet, is that okay, right? I think that, I know you talked about in your presentation, all the way from design to the field, and Ronak did the same. So what are we doing in design side to kind of catch some of these? If you can talk about it. No, I didn't ask that question. I said, what are we doing on the design side? The answer is always zero. Yeah. Right.
Is the fact that now we have a different fault model than what we had architecture designed for. So far, in light of that, how do we now start designing with this fault model? And we start actually abstracting this to something, let's say something similar to the we start with right? How do we actually accommodate this to us prior design? How do we try to design to actually accommodate these faults in a way that still delivers the performance and energy efficiency which is acceptable to that scale to use it?
That's an open question. We don't really have access to economic mathematics. In fact, there was research on a lot of these markets that happened about investment and practice on it and just really important. I think now is the time. It's a good time to actually reignite that time once again and start moving in that direction.
Okay. Thank you, Ronak.
Yeah, let me just add a little bit to that. You talked about cosmic rays in your opening section. And I think one of the questions we even get internally is, hey, we've done all this work for soft error rates. Why doesn't that work apply here? And I think the key is that there's a lot of soft error rates that we can, that when we decide what to protect, it's about the ADF, like we just mentioned. So if you have some structure that's used, let's say once a day for a couple of cycles, you could say that the probability that a cosmic ray is going to hit you at that exact point in time is so low that the benefit of protecting that structure is not worth it. With this kind of issue with defects, that's not the case anymore. If it's used once a day, and that once a day causes it to be wrong, that's not something that we can tolerate. And so I think the cost or deciding where we draw the bar on what we protect has changed dramatically when we look at this space versus what we were doing previously in soft error rate space. So from a design standpoint, the way we think about what to protect has to change. Essentially, we have to go back to what, again, we used to call mission critical systems, which is you must protect everything. In the absence of protecting everything, you have to rely on things like diagnostic tests and so forth. But I think the expectation is the hardware should detect if something bad is happening. And that requires protection, and protection will be costly. So I think coming up with what are the better ways to do protection in a way that is power area cost sensitive is another interesting area to focus on.
Thank you, Ronak. I know like Rama talked about the cost of finding these in the fleet. I think there's a real cost to like kind of, putting in protection around it as well. So I want to make sure like, at least we are all aligned that this is the rates that we are seeing is not acceptable and all of us need to do something about it. So let's, sorry, please.
Quick point I do want to make. Yeah, there's a cost to protection and making sure it's reliable. But I'm confident that there are ways to minimize that cost also. But first we need a solution, then we can worry about how to make it more cost efficient. I think even the lockstep execution, if that capability is there with the ability to enable it and disable it dynamically, we can run it with lockstep enabled for the first 3 months in production. Flush out all the bad parts. If in the second and third month we are not seeing any fallout, we can disable it, right? But we'll have caught everything in the first month. So the cost of these things will be easily amortized quite dramatically. I don't think we should preclude any solution for better protection and more reliable solutions, because there are very creative ways in which the cost can be reduced. And follow up.
Yeah, it's a quick one.
So I think it's a good point that you made, right? So the last step is a novel solution that improves the concept of implementation, right? So if you again go back, going back to what is important here, right? So this community, right? Look at how to make lockstep paying, how to not lockstep paying to look at software. This is what I think early 2000s, a lot of research was. It was one was the second question was how do you like us to follow with question? I think the first question is again something we should ask here is like is lockstep as we know it the best thing that we did is that how does that accomplish the problems with the proven in the field? Are we convinced of that? Right? And I'm not sure we are yet. I think it needs to be investigated. Because, for example, if certain faults are getting activated in defects because of, let's just say, code execution in a certain way, the code executions are identical as far as the message before. So we're actually activating do we need a different way in which they need to actually execute to surface that so that we can do what you said, that you can actually catch in those first 3 months. I think that needs to be investigated.
Yes, but I think anything would be better than black box testing that we are doing right now, right? So I think it's a good approach that we need to focus on. So, but I want to move to the next area, right? And that's important as well. We are doing a lot of testing, we're doing a lot of efforts, but are we doing enough? I want to turn it over to like Carolyn and Sean to like answer that. Are we doing enough as a community? This is a serious problem. Carolyn, what do you think? Is the industry doing enough? Is it giving you things that you need for research? What should we be doing differently?
So I think maybe there's like 4 grades of things that I think would be helpful for academics to have easier access to. So, like high level, and I'll talk about in more detail, but high level, so like hardware platforms, baseline metrics, and like applications. So on the hardware platforms, like obviously it's helpful to have access to this funding hardware so that we can like run tests, evaluate testing solutions, evaluate resiliency solutions, so on and so forth. And even more so than even just having access to say one-off, SDC vulnerable server, we might have access to maybe like a pool of servers, or a pool of servers where you can select some like fraction of buggy and non-buggy, known buggy, known buggy, known not yet known to be buggy servers. So you can kind of stimulate the same kind of environment that hyperscalers are dealing with to test out solutions. So that's one thing. Next is baselines. So having some comparison point for new solutions with what's being done already. So we heard about the Intel Open Intel Open Data Center Diagnostics DCIM. That has really been really great. Like we've been running that quite easily. It's like well documented. That's a super good starting point. I don't know to what extent it's possible to have access to things like either open source or closed source version of things like Scanner or Ripple or SillyFuzz, like these solutions that industries come up with to confirm this group their state of the art, so we can see are we doing better than that. Maybe ideally if we had some access to some buggy core, having some tests that we know exposes some particular SBC vulnerability on that core, even if we have to localize every possible again. Another thing is sort of metrics, like what should we design for, like what do we care about? So maybe there's like intrusiveness, like if it's a testing approach, like how does it interfere with normal data center operation, or coverage metrics, or false positives? Do we care that much about false positives? Is it classify some more things as being SDC vulnerable? They really don't know anything. Even things like ease of deposit, like how easy is it to localize a bug? Like if we can localize it to the CPU, is that good enough? And we'll just get rid of the CPU, or do we want to localize it to like floating point unit or like some particular operation, things like that? Maybe it's like the scale of the fund is really great. We have sounded correction buffers everywhere. Then we want to be able to say, okay, these are the particular instructions we're going to avoid on this particular CPU. Design compilers and software stack support. And then the last thing is baseline. And so I think like Sarita actually talked about the same kind of idea with the Elixir stuff this morning, is like there's a lot of these applications that industry really cares about, and sort of these at-scale applications are what we care about in this context, or mitigating the impact of SDC errors, and like having access to representative workloads that we can evaluate our resiliency, our approaches, so on and so forth on, I think is helpful, and also for certain application-driven testing. And might have also certifications for certain applications that are less susceptible to particular classes of SDC bugs. Like you can imagine, like a machine learning application maybe be slightly more error tolerant and slightly less, impacted by slightly more resilient to SDC bugs. So we have applications specific both for driving, both for sort of application-driven testing approaches, but also just for value.
Thanks, Carolyn. Sean, do you have anything to add? Like, are we doing, or is the industry doing enough to enable academics to solve this problem?
It's a really, really good question. I would say in general, no. It's very difficult for academics who work in class to try out methodologies. Because ground truth has to be ground truth comes from actually applying these methods to real silicon and getting results, analyzing those results. Now, as of late, it's been easier to get design data, test data, and do analysis. That's happened because this area, right, starting cost comes to Google maybe less money. This is violating their business model. The business model is to sell compute, and compute is working. It's trouble. And the test community has dealt with this issue with automotive and medical. Like those types of parts, those types of safety critical systems are tested much more thoroughly with much more harsh environments. And typically there are no or two before the sleeping hour. So that's how far they'll go to ensure they true, reliable parts for defects. Because those things are out there for years. So, something simple is going to have to happen in this space, this entire solution. But there's my community is bringing in different aspects, testing now, a feature just like area security is going to be optimized in order for these systems to perform well with their expectations.
Thank you, Sean. And this time, Ronak, I'm going to go to you. Intel, AMD, of course, Google Meta are all part of the industry, right? So, and Sean says we are not doing enough. What is Intel doing? What are some of the best practices? What are the things? I know you talked about the Open DC Diag. Are there things that we can make to make research in this field easier?
Well, I think that's a step one. I think the second step is essentially having all of us together across silicon vendors, our customers, and our research partners to try to identify what is the next step in terms of the state of the art. Because it will impact, like we talked about, everything from architecture, architecture design, to the way we build our circuits, to the way we test, to the way we look at our software interacting with that. Do we write software that's more resilient in some cases? So I think the steps here are, as a community, how do we do this? I don't think any one of us can solve this on our own.
Thank you, Ronak. Sudhanva, do you have anything to add?
Yeah, I mean, there's a lot to say there. So many different risk, right? So I think one issue is like Sean, you mentioned, right? There is if you look at the safety, functional safety community, there tends to be some standards and some targets and things like that built around metrics of business. You don't have such things, right? So I think it's an open question as to is there something on that domain that should be covered? Open question, I don't think the answer is there. So then I think part of figuring out the answer, as Ronan said, is we need a lot more stakeholders on the topic. Figuring out what is it. Right? You mentioned about that's actually a very interesting idea. It's actually, I say that's an undiscovered country, what it takes for to do that. And we have something which requires some connectivity. Where when you go along that line, I think what we instructive to do is think about what can having real hardware enable, what kind of research can enable, and what is needed to enable research. And so let's take a couple of examples. Right? So the research question is, what is happening in the field? What do we see? What kind of defects do we see happening in the field? Having just a subset of hardware known to be defects has the risk of more fitting to the problem that we see, right? So what we see in the field really requires going back to scale, to the hyperscale, and then maybe studying the systems more and on. It's great that Google has started doing this information. Now, the other kind of questions to ask about is, how hardware can I want to do some testing research on it? What do I need to do that? Like, for example, I want to, let's say, ATP research to address some reform problems. Quite often you need an access as well. Like, and again, that's proprietary, right? So that's challenging. So the question there is, how do I do such research? Is there anyone, let's say, open source information that maybe some methodologies that the silicon industry can implement and apply upon respective designs, or do you need does this happen? I mean, what can happen in the open community versus things which might have a small group working under NDA or some cloud spending some time doing companies to maybe figure things out, right? So I think we need to explore these questions.
Yeah, you mentioned scale, so I want to turn over to Rama and then go to audience Q&A because we have a few minutes over. Thank you, Rama. Any final thoughts on that?
Great point. Organization for me is that none of us can solve the problem on our own, right? The chip vendors do not have the software stack themselves. The academic community does not have RTL or software. Right? We don't have access to the RTL or what have you. The community at large doesn't have the infrastructure or access to the systems to be able to experiment and evaluate it. So the key lesson here is we need to act together. I think the open PC labs and making all these machines available for the community is a good starting point. Google has open source CPU checked into the open source community for precisely that reason. We need to do a lot more of many of these for the entire community to have access to the infrastructure that is necessary to be able to do advanced research and think deeply about this problem on all levels of the stack to sort of figure out complete solutions.
Thank you, Rama. And I go back to that iceberg view, right? We have found only so much, and we need to find so much more. And as you heard from all the panelists, this is an extremely important problem for hyperscalers, for silicon manufacturers, academics working in this domain. But it needs more. It needs software level. It needs hardware level. It needs everything from compilers over silicon to like kind of work together to figure this out. So with that, I'm going to turn it over to like audience Q&A. So if people have Q&A, I don't know if there's a mic over there, but so if audience has Q&A, maybe we can send something out. Yeah, thanks to the panelists. Hopefully we can have more Q&A.
Mark Hampton from Texas University. So my question is, I didn't really hypothesis for clouds on these approaches. My question is it aliens? Or in all seriousness, is it a problem we can often solve? And the T or is it process variations? Is it timing models? Is it hotspots? We ran a workshop just yesterday, so hotspots are shrinking back or back or worse. So is it a problem we've already solved? Or is it a cause? It's a combination of all of them. I'll start and then the panel can chime in. I think for all the cases we've seen, they aren't new failure mechanisms. They're mechanisms that I think are well known. One of them is the range that we operate our parts on today is probably greater than the range we've ever operated on before. Just look at the voltage and frequency range that a typical part can run at dynamically. How do you test across that range is an increasingly tough problem. And how do you test now with a system level test at each of those points with the test that we have? It's not a problem that can be covered just like trying to run black box applications. So I don't think it's necessarily a case that there's something new in failure modes. It's just that the existing failure modes become harder and harder as we are dealing with some of the issues that we're talking about earlier. We're dealing with defect densities that are different from the process. We're dealing with complexity that's increased in our circuits and in our microarchitecture.
So like one thing I'm curious, my understanding is that is actually a little bit of black magic with find that. Like I guess I haven't there's one meta paper that root cause the whole paper is root cause of bug that presumably took a really long time to do. So like how long do you spend root causing bugs to bother to root cause bugs? You give up and say, we don't care, like we're just gonna use the able to do that. Best practices.
I think there are many theology these is very, very hard. Right? And even determining, can we confirm that this is a hardware bug is very hard. Right? So I think the answer is all of the above, all the reasons that we're not cited. And I think we are far from fully root causing all the issues. What I can
I agree, right? So when let's say an architect just we'll figure out what's wrong here, right? Replicating exactly the conditions in which that thing happens is actually extremely hard. In the marginalities, like where exactly do we shoot to in terms of a lot of different parameters, what exactly constant, what exactly was running and what rotation temperature thing we need to put on the tester, right? And then it's a lot more trying to figure it out. Then so once you figure it out, then you look and look for like what do you see in the network? What's the thing that's possible, right? It's a lot of effort.
Yeah, so I do want to say that it's not all environmental variations though. So I think the benefit of seeing this in the fleet, it's like what Rama said, right? It's all of the above. The variations one might be the one easier to kind of look at or like focus on first, but there's even more deeper, even more all the way from design to manufacturing to process to like testing gaps that we have seen. Next question.
places. Some of the lessons to be aerospace. I would guess that also as some parts of this problem of science, how it accelerates it, because of failures on test for engineering, doesn't explore.
And if you want to go to
I mean, this goes back to what I was talking about earlier, things like system level redundancy or how a lot of those systems operate, right? Now, the question is, system level redundancy comes with, I'll call it a high cost. So how do we reduce the cost to get that level of protection? That's the problem. You know, like I mentioned earlier, and we have a career number of course. Can I use that to do more checking? I'm going to talk a little bit about how could we use lots of in both pre-production and potentially in production to help us. Can I do that even at a finer granularity within a form? I think these are all kinds of things that we can use, you know, essentially being inspired by what they've done in the past.
So that's yes, absolutely the redundancies that they go through are the kind of things we should evaluate. The way cost to it, we'll figure out how to solve the cost issue. But I'm reminded of a joke that when I was working at IBM, I was working on this parallel file system called GPFS. And then we were told, hey, Boeing is going to use this. And suddenly everyone panicked, oh shoot, Boeing is going to use this, and the testers were working overnight, right? We flushed out a lot more bugs when we knew that, you know, we'll be flying in the planes that this software will be running on. So once people realize the criticality of where it's going, the engineering rigor also matches that. We have to rise to that.
I was going to say, well, this is not like related to the aerospace industry, but I thought that got triggered all day. There's this paper in Micro, I think 2020, and it was on looking at how software level fault models are actually reasonably accurate for deep learning accelerators. And part of the rationale, so you know, based on this idea, based on this observation, they were able to sort of evaluate different design choices in deep learning accelerators and the impact of things like quantization, different things on the overall impact of soft errors or transient faults on the end outcomes of the application. And the reasons for this were really exciting. Were like, first of all, that there is a pretty much like one-to-one mapping between software level operation and actual RTL instructions, which makes sense. These are very like designs, like very specialized in the application, and also the data flow and control flow paths are more stacked. And so I imagine that maybe in some of these like aerospace types of applications, you have a much more highly specialized design in one particular domain, and that probably allows them to take advantage of it. So not totally related to that.
Yeah, I'd like to add to that. I mean, there is a real cost in doing a lot of these redundancy techniques and reliability techniques, right? And traditionally, until we see these numbers, we have not, like, you know, I think maybe Ronak mentioned this. Maybe it was always there. We just didn't, you know, run millions of them together to find out what the number was. Right. Thank you.
What's occurring across these data corruptions? So think about tests. Test is a binary activity most of the time. You have a bunch of chips, you divide those chips somehow based on the outcome test. Now, I happen to think that the chips that fail usually all the clues that you need to understand what's happening on the other side. There's nothing new under the sun. So if you understand those defects, it's more than likely, in my opinion, that there's some defect that's similar but in a different location. Will I ever be able to prove that? Probably not. Because getting access to actually failing parts, examining the way that we would with the PFA, it's just a really hard thing.
Thank you.
I have a general question on how investment can help academia by providing data. I mean, we did talk about a lot of software related functions, but fundamentally, at the architecture level, we sort of need data in terms of activity, which are the portions of the code that we what are the traces across different machines? Those are some things that we want to ask. So, as there been a plan of this, we did talk about it once in our
yeah, so we do that, right? So, Sean, we say data. Do you want? Yeah, so what I'm trying to understand that more kind of, right? So in the past, one is we had first that happened is to characterize, let's say, what the fault model produces once, and then articulation of this, these are real faults happening here, right? And then that kicked off essentially a stream of work on modeling those faults, and then the whole body of previous work, and then which growing, as well as evaluating techniques around it, right? Data did come by later on, right? The free data and the main data was published as well, which gave you then more information about the shape of the failure that you see in the mistake. Right? Do you have any? So I guess the question is, this is a broad open question. Everybody get audience, almost everybody is like, what kind of data would actually be valuable at this point to actually try and work that? Is it more than understanding of the fault model, or do you need like rates? Do you need
I mean, obviously, we would help us in academia, what to and how they would obviously, that's already that's short term. They will not as some of these defects. But in the long term, it's supposed to be there, right? I mean, obviously, there's something happening and things are you also help us to sort of figure out like statistics, right? Which are the instructions that the industry is giving the most of. So those kinds of data is very hard to access.
This is what I was trying to get at earlier, basically, is like, I think for me, it seems like I want more understanding of like the scope and like motivation of the problem. So like, kind of like we were talking about earlier, like having RTL, okay, everyone's can tell like it's like RTL versus having funny design. So if I have funny design, there may be some degree of like testing I can do to try and better like scope the problem myself. Like if I can design better system level tests, maybe using this application-driven approach, like more frequent error checking, I can maybe get shorter bug traces and like localize bugs to like, oh, like every time I have a revision instruction, there's an error. Like I can try and like localize bugs to like reasonably design the course regularly myself, not as good as like Intel or AZ. But maybe I can try and quantify or characterize the problem a little better, or benefits you're getting more information. Is that kind of what you're asking, or?
I think that's
Just one point I wanted to address, you talked about disruptions. I think we've had similar comments from our internal people saying, hey, how do we get hyperscaler code, whether it's for logic bugs or for defects, to really make sure we're stressing the right thing? And I think our realization is there's no magic in what they're running. They're running just a wide variety of stuff. But the one thing you might want to think about from the silent data error side is which instructions eventually need memory computation, loads and stores. Because those tend to, if you have an error there, you tend to run into things like spurious page faults and patches. Whereas for a silent data error that really persists, it's something that really sits in the compute domain. That's why the example that's given, a floating point example or some other vector compute examples, that's where we tend to see the clustering on these kinds of problems because they don't fit into that chain, right? So that gives you one sense of where it's going.
I think one of the things, like, so first of all, is I mentioned small defects, right? Something we see. That is a lot of problem that the vast architecture we really consider that, right? So we just think about a lot of elements, like we have small delays, how do I think about that? How do I emulate that? In fact, UBC had a case on this 10 years ago. And thinking about how to capture that in terms of architecture out of the work. I think that line of work is still valuable to do.
So I think what we're asking is you need a large sample of known bad machines and their logs, so you can study and sort of classify them and what have. It's absolutely true. I think we need to do that as a community, is to share all the logs so everyone can see what others have done, what confirm this is a bad machine, what can we do to improve detecting these not so easy and what have you. So there's a large body of work that we can do. There's also the point that Sean made that PFA analysis to root cause is super hard. And we don't have the complete analysis for many of these. So, but that is another area of sort of where the community can sort of engage and sort of help us make progress.
I want to just add, this is not easy, right? Sharing, I want to just recognize that, like yeah, no, absolutely. Yeah, because I do want to share, right? From Meta side, from Google side, we publish those papers, but it's not easy to share because each of our systems are made up of like many different parts and kind of, we need to run through a lot of things to get that to happen. So I'm open to ideas. We are committed though, across this panel, we are sitting here and saying, hey, we need to do more. We need to do better. We need to shine the light on this problem because, we are not, without the access, without the data, how can you like kind of replicate, right? So it's a great question. I want to say it's not easy though, but we have other moves, right? We did an RFP, we're doing an open kind of approach. We're doing OCP. So if you're not familiar with what it is, it's an open compute project. A lot of our industry members are there. We're going to do more there. So you will hear a lot more. That's it, but it's not easy. Thank you for that.
Just in the spirit of knowing 10 rounds, like, I think one thing that we value for the community here is when you say I need that, it would be useful to maybe think about what kind of data will be there. So think about it essentially as almost think of it like an RFI exercise that requires for information. So if you have hardware, what do I need? Information about the hardware, everything, and then think about that. Once you think about that, we can whittle that down to something we can say, okay, this seems like there's this could actually enable a lot of research. Then we can explore how to do that.
Thanks. For the questions, I think we have almost like on end of like kind of time. We have only 5 more minutes. So 1 minute per question if it's direct. Otherwise, panelists will be available after. So please direct your questions to. Thank you.